Alright, this is how to compute the cross-sectional area of soil loss at any particular sampling point along a trail network. This is useful for both front country parks and forests and any kind of natural surface trail, as well as those particularly for backcountry contexts. Let's get into it. But before we get into the nuts and bolts of the computation, let's talk just briefly about what cross-sectional area is and what it isn't. It is an intensive point measure. So if you have a trail network starting from some parking lot, and there are trails moving out in a branching or a stacked loop configuration, the process here is to understand the condition of the resources that the trail is cutting through, because a trail is genuinely an incision in the surface of the earth, and we have to modify the earth fairly aggressively where we want to run a trail. So imagine we've got this established trail network, and we're going to take measurements at a bunch of regularly spaced points along the way. So in this let's say this is a small neighborhood trail network like we might find around a green earth property here in Carbondale. Let's say that the typical distance between these sample points is 100 meters. And every once in a while, we're also going to take measurements at trail junctions. So in that case, the distance might be, let's say, 50 meters. So generally speaking, 100-meter intervals, and sometimes odd or strange or unique intervals to individual points, like to the end of one of these trail segments that doesn't connect to something else. Okay, that'll come up later, so remember that. What cross-sectional area is not is a continuous measure across the entire surface of the trail system. So if you're a trail boss or a trail crew member, you're going to use CSA to figure out overall resource condition, or total soil loss in this point. But you're going to do it in a point sampled way. And then extrapolate forward and back from each of these points halfway to the next point, so that you have some sense of what the trail is like outside of all of these points. Each point is infinitesimally small on this trail network, so we're not continuously measuring the whole thing. We're sampling a bunch of points along it. If you need a continuous assessment of every inch or every centimeter of a trail system, that goes over to the condition class as an extensive measurement. Okay? You assign a condition class to every foot or meter of a trail and use that map in concert with the separate map of points for CSA. So you have full coverage with condition class, and you have a lot more actionable information about cross-sectional area point sampled sites. Those are intensive measures. Okay? Cool. Why CSA is useful is basically down to the idea of we are really bad as human beings at just guesstimating big, complex numbers. And understanding something like, what's the total volume of soil loss? How many cubic meters or how many dump truck loads of soil have been lost on our trail network as a function of poor trail design or infrequent trail maintenance? We could come up with a number, but it's going to be wildly wrong in almost every case. And so CSA is just a way to be objective, it's fairly efficient, and it's highly accurate. That's why it's useful. So, with that said, let's get into how to measure cross-sectional area for each of these sample points along a trail network. We'll use just a single point along the network as our working example throughout. So, consider the surface of the planet. This is a hillside looking from the side, so this is a cross-section of the hillside. Here we can see there's a tree growing out of this sloped surface. We've got some forest forbs or herbs, some ground cover, and then underneath the surface, going down from things like leaf litter, duff, humic material, we've got the O1 organic horizon, so the coarse debris horizon. We've got the O2 horizon, the pulverized or homogenized organic material horizon. This stuff traps water like crazy and makes for very soft, mushy trails. So generally, we want to, when we are considering where to put a trail in the first place, so that we can eventually measure it for stuff like this, we want to cut the trail surface down at least through O1, O2, and typically the A horizon as well, which has a lot of organic material, down into the so-called mineral soil horizons, the B and C horizons. This stuff will stay dry, it compacts well, it's highly durable, and keeps us off of the bedrock, which is not always pleasant to walk on. Okay, so this is our hypothetical hillside that we're going to cut this trail into. And then we go ahead and cut the trail into that hillside, and this is what we get. So we've incised or sliced a sort of a triangle or wedge shape out of this hillside, and the trail is one of the two short sides of that triangle or wedge. And again, it's on the mineral soil down here, where it's going to be much more durable for people to walk on and not erode nearly as much as a trail that people just walk in through the O1, O2, and A horizons. We're going to build this trail to specification so that it has a 2 to 5% outslope. That is, if water hits this trail or hits anywhere in the micro watershed above the trail, upslope of the trail, it's going to be able to flow gently and slowly and not pick up a bunch of soil particles as overland flow. So it's going to start upslope here with our raindrop. Then it's going to flow across the trail, and if it is very, very shallowly sloped to the downslope side or outsloped, with that 2 to 5% outslope, it's so flat and almost level that you can't really tell when you're walking on it that it's sloped. But the water droplets, all they need is anything more than a 0% slope. So 2 to 5% is going to be about perfect for us. We'll mechanically compact using a tamper or a dingo or a skid steer or whatever the surface of the mineral soil tread corridor. And as people walk across that, they're not going to alter the surface of that trail particularly very much. It stays flat. The water over time can continue to flow overland. We want it to infiltrate away from the trail. We do not want water, counterintuitively, to infiltrate in the tread surface. We want it to flow off of the trail. But what often happens is with frost heaving and inappropriate levels of use after rain events, for example, we get this combination of erosion and compaction that are called subsidence. Together, these start to form a cupped out shape in the trail. And so the water, when it strikes upslope or precipitates down onto the tread surface directly, it collects in. It can't flow uphill to the downslope side, as weird as that is. We create a micro upslope on the outslope side, and this berm, as this lip is called, is really good at trapping water and forming puddles and mud. And as we know from the band Puddle of Mudd, it's a regrettable situation in all cases. Moving on. So this situation with the trail having formed kind of a cupped out or a trench type shape is exactly what cross-sectional area measurement at each one of these GPS point locations, this is exactly what this is designed to capture and give you a pretty clear but inexpensive to gather number of what is the condition of my soils as a function of my trails, and how much of this soil have I transported through my trail network downslope to my fishing holes, to my streams, and benthic macroinvertebrate habitat, which is part of the food web for all kinds of desirable sport fishing species and so forth. Okay? So, this is exactly what this is for. Here's how you do it. First, you put a stake in either side of the trail, sort of parallel with the GPS point. So you use the GPS to walk to this spot to sample on the trail, and then you place a stake on either side of this spot, and you stretch a measuring tape across it. You record the width of the total distance from edge of the trail to edge of the trail. In our example here, this is going to be 80 centimeters wide. And you'll see me recording the units. We're going to have to do some unit conversion a little bit later on. Don't worry, the math is easy, but we do need to keep track of these units because it will wildly shift the numbers if we get this wrong. After measuring that width, you want to measure the depth of the actual tread surface at each stake. So moving from left to right with this example, we'll measure a depth of 0 centimeters. We'll call this an incision. The trail is basically like our boots functionally or ecologically serve like knives, incising or cutting down into the soil surface where there was not such a cut before, or it was just the construction cut to build the trail. Anything beyond that is making this trench shape, and that's not good. So our first depth measurement at the left-hand stake is 0 centimeters deep because the edge of the trail meets the surface of the earth in this particular example diagram. Our second incision or depth measurement we're going to call 20 centimeters deep. Okay? And we're going to use this width of, we'll say this particular from the stake to this first point where we are measuring vertically down to the surface of the trail. We're going to call that 30 centimeters offset, or 30 centimeters wide from this spot. And at this point, we now know enough to compute the area of this polygon I'm going to label A. Polygon A is 20 centimeters tall on its deep side. It is 0 centimeters tall on its shallow side, and it's 30 centimeters wide throughout. Similarly, we're going to have polygon B, also a trapezoid, and polygon C, a third trapezoid. So we're going to take these measurements and basically just record them in a very simple spreadsheet format, just recording the numbers and what they correspond to. And after getting the width and these incision measurements and any other measurements that you need to capture separately or outside of this CSA process, things like soil texture or presence absence of muddiness, presence absence of loose rocks, coarse fragments, or presence of roots exposed in the surface of the trail as a tripping hazard or injury hazard to the tree. Once we've recorded all this stuff, now we move on to the next point and do this same process for every other point that we've GPSed along this trail at fixed intervals. Then we get to this point here, our field data table for this imaginary point number 42. We have a width of 80 centimeters, the incision 1 depth, I'll change this 20 to a 15. There we go. And its width from the previous incision measurement is 30 centimeters. Incision depth 2 is 10 centimeters. And its incision width from the left-hand stake is 50 centimeters. Now we've already gone 30 centimeters in measuring polygon A. So the width of polygon B by itself, after subtracting the 30 centimeters of polygon A's width from the 50 centimeters of where we dropped this second incision measurement, right here, that's going to make this 20 centimeters wide. Easy enough. Our third polygon is going to be 10 centimeters deep on the deep side, 0 centimeters deep at the stake side, and because our total width is 80 centimeters and we've already measured 50 centimeters worth of width, that leaves us 30 more centimeters for the size and shape of polygon C. And between these three polygons, which we can compute individually, we'll just add those three up and we'll have a clearer understanding of the total shape and size of this cross-sectional area that has been lost from the horizontal, flat, and almost level post-construction tread surface, the horizontal dotted line in this diagram. Okay, so at this point, we've navigated to our GPS point. We've measured the width perpendicular to the direction of the trail between the left tent stake and the right tent stake by using a stretched out measuring tape or laser rangefinder or what have you, and then used a separate measuring tape to measure down from that width tape to the actual surface of the tread instead of what it was originally constructed to be. We've lost some soil, we've compacted some soil in this place, and now it's a big trench. We've got the characteristic measurements, a total width of 80 centimeters, incision or depth measurements of 15 and 10 centimeters, and the shorter widths, the component widths of each of 3 areas or polygons inside of our overall cross-sectional area shape. So we hike this data back to the office, back to the lab, back to the trail shed, and we fire up good old trusty spreadsheet or GIS table of information, and we just do some basic geometry calculations. This is really 6th grade area of a triangle, area of a trapezoid, area of a rectangle kind of stuff. But let's run through it together just to kind of knock the dust off and remind ourselves how to do this. So for our fictitious point number 42, I've recreated what the data suggests the actual shape and size of the trail cross-section in this spot is. You'll notice that this is straight lines instead of the curvilinear actual trail profile or shape or cross-sectional form. That's because we are approximating with a few measurements what could be done with an infinitely large number of measurements and be perfectly accurate. But we don't need perfectly accurate, we need good enough for management to make informed decisions. So, again, width of A was 30 centimeters. Depth of A at its deepest point was 15 centimeters. Depth of A at its shallowest point at that left tent stake was 0 centimeters. So this is a special kind of trapezoid called a triangle. You may have heard of them, where the 2 parallel sides are, in this case, the 15 centimeter long side and the 0 centimeter long side at the very leftmost edge of this triangle. Down below, we've got a computation for the area of each of these. The area of a trapezoid is 1/2 times the incision depth 1 and the incision depth 2 added together. So you're taking the average of the 2 incision depths and you're finding what is the midpoint between those 2 incision depths and calling that the average depth of this. And then you multiply that by the width that you measured for this particular trapezoid, and we're basically collapsing the measurements of this trapezoid down into a rectangle. So we originally measured a trapezoid shape, and this is one parallel side, this is the other parallel side, so those are the incision measurements. And by averaging those two, we get something mathematically more like just a regular rectangle. So this is height times width, and that just gives us a simple area. All right, this is basic geometry stuff from elementary school. So plugging the numbers in, we get 1/2 times 0 centimeters plus 15 centimeters quantity times 30 centimeters. That factors out to 7.5 centimeters, or average incision of 7.5 centimeters, times that width of 30 centimeters, for a total square area of 225 centimeters squared. Not actually a very large area when you get down to it. That's 10 by 22.5 centimeters. Not very big. Let's see. The area and shape of B is a little bit more like a rectangular or regular trapezoid. We've got incision depths of 15 and 10 centimeters. The 15 on this one is the same measurement as the previous trapezoid's deeper or second measurement. We have 2 trapezoids sharing a side. Okay, so if you're not sure where these numbers are coming from, that's precisely it. So 15 centimeters plus 10 centimeters divided by 2 times that width of 20 centimeters gives us a total area for polygon B, the middle of the trail, of about 250 square centimeters. Likewise for C, computing it all out, a 10 centimeter depth plus a 0 centimeter depth, averaging out to 5 centimeter depth, times 30 centimeters of width gives us 5 times 30 is 150 centimeters square. Okay? And between these three polygons, now we've got the whole area, or the approximate area, of the total cross-section represented. Good enough. Next, we just add these three areas together. 225 plus 250 plus 150 is 625 centimeters square, which, again, is not actually a very large space. This is a tiny fraction of 1 square meter, as we'll see here in a moment once we do our unit conversion. Righteous. Moving on. Now that we've got the total cross-sectional area of this one slice across the trail, from its post-construction tread surface, which was flat at the top of the trail tread, and has since eroded and compacted or subsided down into a bowed out or cupped out or trenched out or slitted out shape. Now we want to multiply that area that we found in square centimeters against the length halfway to the previous point and halfway to the next point that we're going to survey using this same technique, this cross-sectional area measurement technique. And then we're just going to multiply everything together, and that'll give us not an area, but a volume, a total number of bucketfuls or handfuls or dump truck loads of soil that have been moved or sort of disrupted from this system. And so we need to go looking for that elsewhere if we're trying to make sure that our ponds, our streams, not getting silted in or blasted out with sand. Okay, so here's how we do that. Finding total volume, just more multiplication and division. We'll multiply the total cross-sectional area found at this trail sample point by 1/2 of the distance from the previous point. In our example for our trail network, where our typical trail points, survey points were 1 to 200 meters from each other, that would be like 50 to 100 meters as 1/2 the distance from the previous point, and then 1/2 the distance to the next corresponding point after this one that we're headed to next. Again, we want to make sure to never miss converting our units so that we're speaking apples to apples. All right, so let's do that first. Let's convert 625 square centimeters that we computed as the area of cross-sectional soil loss subsidence at this particular sampling point. We'll divide that 625 by 10,000. There are 100 centimeters in 1 meter, and a meter squared is 100 by 100 centimeters. That's where we get the 10,000. 10,000 is 100 times 100. So we divide 625 square centimeters by 10,000 square centimeters to figure out how many meters squared we are looking at. And that is 0.06, 6% of 1 square meter in this 80 centimeter wide trail that's 10 to 15 centimeters eroded down. Okay? So again, a pretty small area, but we then multiply that fairly small area, that 6/100ths of a square meter, 6.25% of 1 square meter, times half the distance from the previous point at 100 meters, so 50 meters resulting, and 1/2 of the distance to the next point, hypothetically, let's call it 200 meters. So we're looking at a total of 150 meters multiplied against our 0.0625 meters squared. That gives us 56.25 cubic meters of soil lost in this area. That's a lot. This is 56 cubic meters of soil. That might be a couple of 100 tons if it's a heavy, dense, heavily consolidated soil. in one single segment of trail that is just 150 meters long. That is like a 5-alarm fire. That is a huge amount of resource destruction and loss. So let's put this in context for your trail crew. To help them understand the gravity of the situation, we're going to divide that 56.25 cubic meters by about 16 cubic meters. To answer the question, okay, so it's hard for me to picture what is 1 cubic meter of soil and what that really means. But everybody knows how big a dump truck is. We're talking about for this one section of trail that's 150 meters long, not particularly long, we could walk it in a minute or two, we'd have to bring in 3.5 whole dump trucks of soil, of fill material, to repatriate or refill this area. That is an absolutely insane amount of work, okay? So, even if you're getting relatively small numbers for the cross-sectional area at any given point, keep in mind you're extrapolating forward and back from that point, halfway to each of the neighboring points, and turning that cross-sectional area into a volume. And the numbers get real big, real fast. Now, imagine for a major national park, a major wilderness area, where there might be 1,000 to 2,000 of these points. And the sampling interval might not be 100 to 200 meters, but 500 meters, going about 1/3 of a mile in between points. Okay? So, 3.5 dump truck loads times, let's say, 2,000 points. Well, is it even possible, is it conscionable to have to, in a wilderness setting, backpack in or mule train in 7,000 dump truck loads of soil to repair the damage to the trail network? No, it's not going to happen. That's not even feasible for a major organization like the United States National Park Service. So, this is why we collect this information. We have to find these eroded areas while the numbers are significantly smaller than our example here. This isn't a huge trench that we've measured. This is 6.25% of a single square meter of area, of space. And it ends up being thousands of dump truck loads across an entire trail network. Okay? So, this is one of those where there's smoke, there's fire situations. And we have to catch this stuff before we hit this terrible, terrible outcome. Okay? So, that is how you measure cross-sectional area and why it's important.